Okay, trig identities. This is often a highlight for students in advanced functions because it's fun, it's like a puzzle. With trig identities, there is no algorithm, there's no set of steps that you are to follow in order to complete your task at hand. So what I'm going to do is I'm going to give you some tips, strategies, and I'm going to solve a couple just so you can sort of see the thinking. Full solutions will be available to all questions on the class website, but for now, let's just dive in. So a trig identity is essentially you're given a question similar to our example one here, and what you need to do is you need to prove that this is indeed true, that the left-hand side does indeed equal the right-hand side. And the way that you do this is by using identities that you already know. So the Pythagorean identity is that one, the sine squared x plus cosine squared, I'll use theta, is equal to 1. That's our Pythagorean identity. And in previous videos, we've seen compound angle identities as well as double angle identities. The other one you might want to remember is that tan of theta is sine theta over cosine of theta. Things that you want to keep in mind when you are solving trig identities, you must have a left side, right side proof, and I'm going to show you what I want that to look like in each of the examples that I do. Essentially, you set the left side equal to whatever, right side equal to whatever, and then you continue. You must work on each side separately. There is no moving things to the other side. That is not how proofs work. You have to stay within the left-hand side and the right-hand side. A couple of key strategies here. When in doubt, you want to change everything to sine and cosine. It just makes it a little bit easier if you get rid of tans, if you get rid of secants and cosecants and stuff. You also want to try everything. Can you simplify? Can you expand? Can you factor? Can you do anything here? Like, help yourself out. Just try. Okay? And my advice to you is to start with whichever side looks more complicated and then somehow get it to match with the side that is less complicated. Okay? What the other thing I will say is that there is no correct way of completing a trig identity. You are not allowed to break math. Okay, you got to follow those rules. However, you can do it in lots of different ways. So I'm going to show you one method of solving each of these identities here, and then I'm going to give you a bunch of questions that you just have to try on your own. And I'm going to show you one way that I come up with in solving the identities, but maybe there's other ways, and that's okay. Last but not least, I want to make sure that you are finishing your proof appropriately. We're going to use the since left side is equal to right side, therefore QED. Okay, let's just zoom in here. This is our since. QED, some people also write a box instead. It's like a blank box that you put a check mark in, being like, yeah, I'm done. QED is just like, I proved what I told you I was going to prove. It's Latin. And I did look it up. QED is quod erat demonstratum, which basically means I proved what I told you I was going to prove. Okay? I'm going to do 4 examples total here today. Again, there's no one right way of doing it. And you just sort of have to dive in and see what you can do. Let's look at our first one here. Prove that tan of theta times cosine of theta is equal to sine of theta. First things first, I need to separate them, and I need to do my left side equals and my right side equals. In this case, my left side is equal to tan of theta cosine of theta, and my right-hand side is equal to sine of theta. I think it's pretty obvious the left-hand side is the more complicated one, and so that's where we're going to start. I need to manipulate this somehow so that it equals to sine theta. Not totally sure how I'm going to get there, but what I am going to do is I'm going to follow that one step and put everything in terms of sine and cosine. So my tan, I'm going to change it to be sine theta divided by cosine of theta, and this is still all times cosine of theta. Well, look at that. My cosine of thetas will end up canceling out, and so my left-hand side is equal to sine theta. My left-hand side now matches my right-hand side, so I'm done. And so I can conclude with, since my left-hand side is equal to my right-hand side, therefore QED. Okay, that was pretty easy, right? A little bit of massaging, a little bit of manipulating. Example number 2. Prove that sine theta plus cosine theta, all squared, is equal to 1 plus 2 sine theta cos theta. First step, always separate them. My left-hand side is equal to sine theta plus cos theta, all squared. And my right-hand side is equal to 1 plus 2 sine theta cos theta. It's not totally obvious to me what I would do on my right-hand side. Everything is already in terms of sine and cosine, and I can't really factor here. So I'm going to take a look at my left-hand side. And the only thing I can really think to do would be to expand. So that's what I'm going to do. And see where that gets me. Sine theta times sine theta will be sine squared theta plus sine theta times cosine of theta. So I did that one, now I'm doing that. Then I'll do cosine of theta times sine theta. And then I'll have a cosine squared theta when cosine times cosine at the end. These two terms in the middle here are the same. And so I'm going to just combine them and write 2. And that's not far off. We've got a 2 sine theta cos theta on the right-hand side, so I've got that here. And then the other thing I can notice is I can probably use my Pythagorean identity because I have a sine squared plus a cosine squared. I'm just going to rearrange that so they're right beside each other. And our Pythagorean identity says that, well, sine squared plus cosine squared of theta is equal to 1. And look at that. My left-hand side is equal to my right-hand side. I have been able to manipulate my left-hand side to get it there. So I'm all good. I can say, well then, since left side is equal to right side, therefore QED. Okay, lots of other examples for you to try, but I'm going to move on to a compound angle trig identity now. And this is a compound angle one because it relies on us using the compound angle formulas. First things first, always, I'm going to separate them out. My left-hand side here is sine A plus B plus sine of A minus B. My right-hand side is equal to 2 sine A cosine of B. Doesn't look like there's a lot that I can do on the right-hand side, so once again, I'm going to simplify the left-hand side, and I'm just going to expand these based on the formulas for compound angle. So our first one here is I've got a sine with a plus, and that's going to break into, remember it was a sine of an angle, cosine of the other angle, and then the symbol remained the same, so in this case it was a plus. And then we did cosine of the first angle times sine of the second angle. So these two match up. And now I'm going to expand my second one here. So there's going to be a big old plus. And then once again, our sine, so this is a sine formula with a negative. So I'll do sine first angle, cosine second angle, minus cosine first angle, sine second angle. So I've expanded everything here. Now let's see if I can simplify. Looks to me like I've got a sine A cos B twice. So let's combine those to be 2 sine A cos B. And it also looks like I have a positive cos A sine B and a negative cos A sine B. So those will actually cancel out. And look at that. My left-hand side, 2 sine A cos B, is now equal to my right-hand side, 2 sine A cos B. Perfect! Since left side is equal to right side, therefore QED. Okay, this is a simpler one, but we got there using the formula. Okay, let's do a double angle one now. Prove that sine of 2x divided by 1 minus cosine of 2x is equal to cotangent of x. Split it up. Left side. Sine of 2x divided by 1 minus cosine of 2x. And my right-hand side is equal to cotangent of x. Right away, I'm going to change my right-hand side to be in terms of sine and cosine. That's just going to be easier for me. Remember, it's the inverse of tan, so it's cosine of x divided by sine of x. Okay, now let's do some expanding on the left-hand side. That one's definitely the more complicated one. Let's get rid of these double angle formulas, and let's just put things in normal terms. So the double angle formula for sine of 2x is 2 sine x cos x. And then there were a couple of different formulas for the double angle of cosine. What I'm going to do is, it looks like I need a cosine on my numerator, and I already have that here. What I also have on my numerator on the left-hand side is a 2 sine, and on the right-hand side, it needs to end up with a sine in the denominator. So what I'm going to actually do is I'm actually going to pick the version of the cosine double angle formula that's got a sine squared in the denominator, so that I have more sines on the bottom than I do on the top, because I know that that's my end goal. Okay? So in that case, the double angle formula that I'm going to pick for cosine will be 1 minus 2 sine squared of x. Okay? I'm going to clear up my denominator here and just sort of expand this. I'm going to have a 1 minus 1, which is just 0. Actually, I'll do this. 2 sine x cos x. Let's distribute that negative out. Oh, not theta x. There we go. So I'll have my 1 minus 1, which will cancel out, leaving me with a 2 sine squared x in my denominator. 2's cancel out really nicely, and as I had hoped, my sine x on the numerator will cancel out with my sine squared x in the denominator, leaving me with cosine of x divided by sine of x. Yay! Our left-hand side is now equal to our right-hand side. Therefore, Q, E, D. And we're all done. So that's the gist. You just sort of massage things, you manipulate things, you see what you can do, and try to get your left-hand side to be equal to your right-hand side. That's the gist, everybody. There's no one right algorithm to follow. It just takes a little bit of practice, okay? You got this.